Big data is difficult to classify. So we're going to be looking at some very important concepts and terminology in this video as we look at classifiers and big data that leads to classification problems. Again, we're going to have some important concepts and terminology here. May want to revisit this from time to time. We're looking at the math, starting with variables. Variables can take on different values. A variable that takes on its values predictably is called a regular variable. If unpredictably, that's a random variable. A feature or factor is a variable that can be sampled from which we can obtain data. A model is a function. By that we mean that we have an instance or sample of input and state variables, then that corresponds to a unique output. An algorithm is a model in which the functions are procedures. A computer program is the implementation of an algorithm using data structures, and if we use a programming language, then we call that coding. Regression versus classification. Regression means we're using existing data to predict future numerical outcomes. So linear regression produces a line that can predict outcomes for inputs not in the original data. Regression often, but not always, requires assumptions and a model. Our focus is going to be on classification problems. Each observation in the data is in a class, and the goal is to predict the class of any new observations. Classification problems is where we have categories or classes, and each observation is in only one of those. The class to which an observation belongs is its label. The problem of identifying or predicting the class or label of a new observation, which is unlabeled data. This is the problem that we try to solve with classification problems. Typically we say class 0, class 1, class 2, so on and so forth. A classifier is an algorithm which predicts the class of an unlabeled observation. So observation, predict a label. That's a classifier. For example, digit recognition. So we'll have a whole bunch of observations of handwritten digits, and each digit is in one of 10 classes. We try to predict the class of that handwritten digit. We're going to focus on two classes, class 0 or class 1. Also sometimes positives, class 1, or negatives, class 0. We're going to do so because it's usually fairly straightforward to extend to more than two classes. We'll see that later with the digits data. There are some algorithms that we will introduce as multi-class from the start, however. A binary classifier is just a classifier with only two classes. And the reason we like to focus on binary classifiers is because of their nice interpretation in terms of predictive models. What is the probability that an unlabeled observation is class 1, or a Bayesian confidence? This is a predictive model, and it's also a binary classifier. So if we have a binary data set with only 2 or 3 numerical features, then we can visualize those as points labeled by the class, as you see here. Can we predict the class of an unlabeled point? To do so, we start out with some definitions. The convex hull of a set in the vector space Rn is a set of all linear combinations of the form alpha p plus 1 minus alpha q, where alpha is in the unit interval. And that is actually what's known as a line segment. So it's the set of all line segments between points P and Q in our original set. So if here's P and here's Q, then as alpha goes from 0 to 1, we get a line segment. The set of all line segments gives us the convex hull. Now there's a theorem that says if the convex hulls of the classes of a binary data set do not intersect, there must be a hyperplane, a concept of a plane in an arbitrary dimensional vector space that separates the positives from the negatives. And when we have this situation, we say that the positives and negatives are linearly separable. Now, this theorem actually we prove in convex optimization, which we do in operations research too. And we're going to use this theorem, but that's the class where you really see it. So a classifier problem with two classes is linearly separable if there's a line that separates the data. So if we have XY coordinates and we can draw a line that separates the positives from the negatives, then the data is linearly separable. So if we have linearly separable data, then we mean that we have convex hulls and they're disjoint. It means there's a separating hyperplane. It also means that there's a thing called a margin. In other words, a region between the two convex hulls. A predictive model is a heat map on the plane. So here's my predictive model. And what this model means is where it's green to the left of the first pink line there, that's a prediction of probability 0 that that point is in class 1. Now on the right, I used gray, so I wouldn't cover up the numbers. And on the right, we have probability 1 of class 1. And then in the margin, we have a gradual change from 0 to 1. So numbers like 0.3, 0.5, so on and so forth. And if we include convexity, we can get an even better predictive model. But we want to say separable only if linearly separable or if we can transform into linearly separable. The reason is because if you have arbitrary curves, you can get arbitrary predictions. So notice that here is an arbitrary curve and it's going to separate the data. But I can do another arbitrary curve and separate the data. Both of those do the same thing, but they're arbitrary. The red point is in different classes, depending on which arbitrary separating curve I use. But there are some data sets that are clearly separable, just not linearly. Now, what that means is that we can transform the data. We're only going to allow linear separation, but we can transform the data. In this case, we use log-log space, and sure enough, that gives us linear separation. We may be able to define new variables. So for instance, here we have polynomially separable data. The curve z equals x plus x squared separates the data. And if we let y be equal to x squared, which means the x factor is squared to give us the y factor, we get z equals x plus y, which is a plane in 3 dimensions, as you can see here. So we define a new variable, we're in a higher dimension, and we can separate with a hyperplane. This is linearly separable in the higher dimensions. So if we transform to get linear separable, that's okay. But nothing other than linear as a separator. No arbitrary curves. So we can use dimensionality, and this is often what we do. So data that cannot be linearly separated in 2 dimensions may be separable in 3 dimensions. I know I'm kind of repeating myself, but this is an important idea. Data not linearly separable in m dimensions may be linear separable in greater than m dimensions. And very often, this greater than m dimensions is infinite. In other words, we use an infinite dimensional vector space. Here's an example, a famous example. The XOR is not linearly separable in 2D. So if we think of 0 as false and 1 as true, then the logical X and Y data looks like that, X or Y, and the XOR means that if the X and the Y are the same, you get false. So clearly this is linearly separable. The AND is linearly separable. The OR is linearly separable, but the XOR is not. But the XOR is linearly separable in 3 dimensions. So notice that what we can do is we can define a new variable z, which is x plus y mod 2, and that gives me a 3-dimensional representation, and sure enough, we see that we have linearly separable. So linear separation is important, but it often is also impossible. So the multi-scale nature of big data can make it impossible. Why? There may not be any linear or any transformation which creates linear separation, or at least not an obvious one. Convex hulls may always intersect. For example, microarray data. So we may have a class 1 of genes activated by an experiment and class 0 not activated by an experiment, and the data looks like this. It's not linearly separable. There are some other examples of non-separable classification problems. Here's one using whether or not a decimal expansion it contains the digit 1 with a frequency greater than 0.25. This is the binary expansion. And we wouldn't think that would be separable. Newton's method, again, not separable. So, because it's often impossible to linearly separate between classes, we simply have to trust that we may not be able to separate. But algorithms that learn often do not need separation. For example, nearest neighbor algorithms are simple, useful, and robust, and the starting point for all learning algorithms. For example, to predict the class of this unlabeled point in red, let's zoom in, and then let's look at the neighbors of this point that already have labels. So here I picked out 4 neighbors, the 4 closest neighbors. And if I use weighted voting, and for example, if they all have a weight of 1, then there's a 75% probability that it's positive. Or I could say, well, let's use the actual distance to weight the vote. But however we do it, we have a way of doing classification without requiring separation. It's also useful for regression, and very often we use nearest neighbor methods for regression as well. But nearest neighbor and learning algorithms in general, we get what I think of as an embarrassment of riches. Nearest neighbor methods can get, quote, out of control. Too few neighbors, you get errant predictions. Too many neighbors, also a problem, as we'll see later. Testing and validation are crucial for nearest neighbors and for learning methods in general. Linear separation is based on powerful mathematics, convex optimization, which you learn in OR2, and we'll use it in this course because it's very powerful. But I'm not going to require you to know anything about convex optimization. I'll point it out when we use it. For those who know it, it'll be useful to know where the convex optimization shows up. We're going to focus on nearest neighbor and learning methods that are going to be built from scratch in this course. No background required for any of these.